This video introduces the direct synthesis method for tuning feedback controllers. The first step in the direct synthesis method is to model the closed loop process. We might develop a closed loop process model using a block diagram like the one shown here that was introduced in the previous chapter. Next, we choose how we want the feedback control loop to track set point changes. For example, we might choose that we want the feedback control loop to respond to set point changes with first order kinetics, first order plus time delay kinetics, or second order plus time delay kinetics. If the feedback control loop contains a time delay in any of the transfer functions, then we must include that time delay in our model for how the control loop should track set point changes. Then we solve the servo transfer function for the controller settings that will give us the desired response. Recall that in a feedback control loop, the response of the controlled variable y to set point changes is given by what we call the servo transfer function. The servo transfer function has in its numerator the product of every transfer function in the forward path between the set point and the controlled variable output, and in its denominator 1 plus the open loop transfer function, where the open loop transfer function is the product of all of the transfer functions in the feedback loop. In the foregoing discussion, we'll assume that the measurement transfer function is represented by the gain Km. So Km and Gm are equal. And then we will factor out the controller transfer function, Gc, from the open loop transfer function, which is this product, and we'll call that group of transfer functions with the controller transfer function factored out, G. So G here represents GV, GP, GM. And it's also equal to GV, GP, KM because GM is just a gain KM. Having factored out the controller transfer function, GC, we can now solve for the controller transfer function as a function containing G and y over ysp, which is our servo transfer function. Since we have not tuned the feedback controller, the servo transfer function is unknown. That means we get to choose what we want the servo transfer function to be. We'll call it y over ysp with a subscript d to indicate that this is the desired servo transfer function for the feedback control loop. Now, in order to tune our feedback controller, we may also need a model for G if we don't know it exactly, or if we want to make approximations. So we'll call our model for G, G tilde, which is how we expect the process, the valve, and the measurement to behave, even if we don't know exactly how they will behave, or if G tilde contains approximations. Now we can write the controller transfer function as the reciprocal of our model G tilde times this ratio of the desired servo transfer function to 1 minus the desired servo transfer function. Now, in the ideal situation, we want good set point tracking. That is, when we make a change to the set point, we want that change to be represented in the controlled variable. And the ideal case would be if that happens instantaneously. So if the servo transfer function is equal to 1, then we obtain perfect set point tracking. The controlled variable will always be exactly equal to the set point. But that's actually impossible, because all real processes contain time constants and time delays. Instead, we might more reasonably expect that the servo transfer function will behave with first order kinetics, or even more realistically, first order plus time delay kinetics if our feedback control loop contains a time delay. If our first order control loop contains a known time delay of value theta in any of these transfer functions, the valve, the process, or the measurement, then that value of theta must be included in the desired servo transfer function. We'll call the time constant tau c to indicate that it's the time constant for the controlled process. Now, if we insert the desired ratio of the output to the set point, that is the desired servo transfer function, into the formula for the direct synthesis method, we can multiply by tau cs plus 1 to simplify, and we obtain a controller transfer function that has a time delay in both the numerator and denominator. To deal with the time delay in the denominator, we will approximate it using what we introduced earlier for the Taylor series expansion of the exponential. The resulting tau cs can be combined with the theta s in the denominator. We will use this controller transfer function equation to design several controllers. Let's start with an FOPTD process model. So our G tilde is an FOPTD model. Remember, G tilde is a model for the product of the process transfer function, the valve, and the measurement, and any other transfer functions that might be in our feedback control loop, except for the controller. If G tilde is an FOPTD model, when we insert the reciprocal of G tilde into our design equation for the direct synthesis method, note that the time delay in G tilde cancels with the time delay that we have in the numerator of the direct synthesis controller equation. This is why we always want to include a time delay in the direct synthesis method if our process has a time delay. With a little bit of algebra, we can rewrite this controller transfer function as a constant multiplied by a 1 plus 1 over tau s term. You should recognize this functionality of s as a PI controller, where this group of constants represents the controller gain, and tau represents the reset time for the integral element. So if the process model G tilde is an FOPTD model, then a PI controller will give the desired feedback control response. The reset time tau I should be chosen equal to the time constant in our FOPTD model, and the controller gain Kc is based on the gain, time constant, and time delay of the G tilde model, and the desired value for the closed loop response time constant tau c. This time constant for the desired closed loop servo transfer function response becomes the adjustable parameter to tune the controller. We can choose to make tau c large or small, but usually we choose a tau c that's smaller than the time constant for the open loop process, or smaller than tau. Next, let's consider a process model G tilde that's SOPTD. If we have an SOPTD model for G tilde, we can substitute its reciprocal into our design equation for the direct synthesis method. Again, with a little bit of algebra, we can show that our controller transfer function contains a constant term, a term multiplied by 1 over s, and a term multiplied by s. And of course, you should recognize this as a PID controller, where the derivative time is the product of tau 1 and tau 2 divided by the sum of tau 1 and tau 2, where tau 1 and tau 2 are the time constants in our SOPTD model for G tilde. The integral or reset time is the sum of tau 1 and tau 2, and the controller gain is determined by the gain, time constants, and time delay of our G tilde model, and the one adjustable parameter tau c, which is the time constant that we choose for the FOPTD response of the feedback control loop. Again, we can choose tau c to be large or small. Typically, we would choose tau c so that feedback control loop responds more quickly than the open loop process. That is, tau c is usually chosen to be smaller than the dominant time constant in the SOPTD model. The direct synthesis method has limitations. For example, what would happen if our G tilde had a right half plane 0? Well, if G tilde has a right half plane 0, when we take the reciprocal of G tilde, that 0 becomes a pole in the controller transfer function. We would not want to tune a controller that has a positive pole, because that would make GC an unstable transfer function. So instead, we'll use what's called the internal model control method. The IMC method is introduced in the next video.